Thank you for coming. This presentation is about DAGonStar. DAGonStar is a scientific workflow engine. Yes, another scientific workflow engine. And let's motivate why DAGonStar was born and what are the applications DAGonStar is using. First of all, what is the motivation for our effort? We are really peculiar setup in our data center because we host two tier-level machine, three-level machine, one for scientific research and one for production. But for production of what? Since 1999, we run officially or not officially, it depends by the time, a local weather service, orchestrating different models. In the past, CMMMA, then WRF, and then the family of models orchestrated in the production graph and graph and graph. And essentially, we run routinary tasks. That means the workflows are application completely unattended. The start of the workflow is determined by the availability of initial data. Everything has to be working as much as possible in a really smooth fashion without the need of a human intervention. Then on the other side, we have another kind of application running on the same machine that are on-demand application. In this case, these applications have a user interface, a really simple user interface, because are used in real-world tasks by local administration, essentially the local health organization, and those people are completely no understanding of computation, no understanding of HPC, and actually no understanding of workflows. They have to solve their problem and provide as fast as possible answer to the decision makers. And this kind of application is a class of application of scientific workflows where external software are the keys. That means, yes, there is the workflow engine that is just an orchestrator, but then the external software is very diverse and different, really often considered a kind of legacy by the related communities because no one wants to touch a code with maybe 30 years of development history in Fortran that have to just work because it is working and because they are experts in that community that are super good in developing this software. And this kind of software are usually producing and consuming large files or group of large files. And really often the number of files produced or ingested by each task is unknown unless at the runtime. So you cannot map easily the input and the output as in other situations. And above all, about this peculiar behavior, actually, we don't know if a task fails, but not in a really destructive way. Just for example, a model can blow up because initial conditions that might be are overstepping the CFL conditions, and the application have to be fail-safe a lot fail-safe because even some computation that is not performed till the end is good to continue the computation if results are consistent. But so actually, it's not just a question about checkpoints because kind of really relaxing condition of failure. And then the magic for buzzwords, replicability, reproducibility, reusability, and fairness in this kind of conditions are not buzzwords or nice labels, are something that we need because this kind of application has to be as much as possible replicable, reproducible, and above all, data producers have to be fairness. Here we have to be fair, and here we have still a lot to work. And this is the kingdom of co-design, because from the application requirements, we have to move to middleware features, and of course, vice versa, even often involving the design of the actual ACP, HCP machine. And this is one of the applications. This is a routinary. This is the application we run since 1999. Of course, software changed, models changed, but the idea was almost the same. We run really local and high definition weather forecasts that are used by the decision makers, of course, for sporting events and other for sporting events and so on. This is the workflow of the application. We have a typical setup in which when initial conditions and boundary conditions are available, starts the work for weather research and forecast model preparation. This is an external software. This is a kind of software that's used almost as is. We cannot modify the software. We cannot change some behavior unless we are expert, of course. And then we run the WRF. WRF is really demanding from the HCP about the high performance computing needs, especially at this resolution. We run the WRF at 1 kilometer resolution. Ground resolution is actually one of the highest resolution in routinary computation in Italy. Once WRF results are computed, we use WRF results to drive, to couple with two other models, both marine models. One is the regional ocean model for coastal dynamics, and the other one is a wave watch tray for sea waves driven by winds. Actually, the resolution of a WRF is 1,000 by 1,000 meters, and the resolution of the wave watch tray is 300 meters by 300 meters. But what is really impressive and computational demanding is the resolution we use with the regional ocean model. That is 135 meters by 135 meters for almost the domain shown in this picture. That is pretty big because the full Campania region is 300 kilometers northwest to southeast, and the extension seaward is 60 miles, 120 kilometers, about 120 kilometers. And this is our signature application. This is a pretty ambitious project that now finally ended from the research point of view. Actually, not ended, but now it started in the maintaining state, and the local health organization pays us to take up and running the system. Actually, the target of this application is predicting bacteria contamination in farmed mussels. It's a pretty challenging task because there are some implications related to the health of the population. So we want to know in advance if the mussels destined to the as a human food could be contaminated or not. Because if they are contaminated, cannot be sent to the market. This is right. But how it works from the legal point of view? Because the policymakers usually don't follow uh, what a scientist could think. Basically, now it works in this way, at least in Europe. Each 2 weeks, the local health organization check the muscles. And if the check is positive, it means contaminated, the muscles gathering is stopped for 2 weeks. And then the sample is repeated again. If it is checked contaminated, still 2 weeks of no gathering. You know, people involved in this kind of business usually are not, I could say, are pretty uh, okay. They don't want to stay 2 weeks without working, and it could happen that these untracked contaminated mussels come to the market. And the local health organization don't want this. So they asked us to create a model to predict this contamination. And finally, at the beginning, we provided a tiny model focused on the uh, Bay of Naples and tracing the fecal contamination using a Lagrangian model and providing the results as a forecasted concentration of inert that could be assimilated as a pollutants that could be interpreted as an index of contamination. Actually, was not good, and finally we refined our target using AI. We produced the results. This is the big picture. Basically, we have the weather conditions. The weather conditions are predicted by WRF, and then the weather model is offline coupled with the dynamic model, the ocean dynamic model. The ocean dynamic model produce the sea current field that used to drive particles released by fecal sources. The particles are assimilated as a pollutant, and then finally we use an AI model that basically predicts the bacteria contamination, considering a trained model trained on the actual measurement performed by the local health organization. This application is really demanding because I have just to work, and we have we have a contract. We have to be sure that it is working every day. This is the workflow of this application. It's as you can see, is a mix of regular computational models up to the Wacom plus plus, that is a Lagrangian model, and then iQuant plus plus is an AI based model. To orchestrate this, we need something that is rock solid, that could work unattended, and so we need a tool that is designed to manage this kind of application. This is another application that actually is on demand. It's really similar to the previous one, but in this case, the study area is different. This is in northeast of Italy, and this project was founded to check if what we did with the Campania region is applicable also in other places of Italy. And okay, spoiler alert, it works. It is applicable too. So just continue to the application we need to work in that we need to make working in a really stable fashion is this other one. This is for arson and wildfires. Basically, this application is used by the local environmental agency to check if after a fire or a wildfire of arson, the soil is contaminated. They have a really simple user interface. You can see in this uh, in this slide. The application is implemented using a workflow course, and the workflow is on demand, run directly by the user. Of course, the user has no is completely not aware about the meaning of workflows and submitting jobs and whatever. The user just selects some parameters for the arson of the fire, and then the system performs the computation. When the computation is ready, the user is notified, and data is automatically provided in the fashion that the decision maker have to use to perform its decision. This is a really popular application in the environment of people involved in human health and local health organization. So now let's meet to introduce the hero of the day. The hero of the day is Dagon. Actually, the original name is DAGonStar, spelled in the way you can see in the logo. Of course, DAG is for direct acyclic graph. Okay, no as parallel job on anything because the star could be the wildcard. Actually, after the first publication with the star in the title, publishers were not happy because that, so we changed the name in a star because it became difficult to manage with the papers. And DAGonStar shares some similarities with Parcel, I have to say. Actually, both were presented at SCE in 2017, and it was pretty fun because there was no contact in development between the two groups. Of course, we know each other very well, but this was definitely good. This is science. And Dagon is integrated in the Python environment. Actually, it's different than Parcel because Parcel is based on futures. It's a really nice piece of software, I have to say. I like a lot. While Dagon is based on backward reference. And the Dagon has been designed explicitly for external software. It works also for non-external software, but with external software is definitely very well designed. Improbable, of course, but well designed. The target is even having a minimal footprint in terms of scratch storage. When you run this kind of software, it's, believe me, pretty messy in terms of the amount of storage you need for scratch directory, because these software are really old-fashioned. Really often they produce a lot of data. They're completely not optimized in terms of overlapping input and output. It's really a pretty challenge trying to minimize the footprint in terms of temporary files. The other target is have to be really straightforward, define the task and above all the dependence between the tasks. Dependence intended as files and a group of files, files that are not well known a priori. You don't know if a model that is intended to produce, for example, 72 hours of simulation actually maybe could stop after the first 24 hours because some parameters are stable enough to consider good the simulation up to the 24 hours, but not to go on. But that data have to be used. And the other point is let's say Galaxy, for example. Galaxy is a really nice piece of software. The user interface on Galaxy is wonderful. Basically, you produce your workflows painting with a palette of tools, but is very data centric in terms of where the workflow engine is executed. This is perfectly okay if you run Galaxy, for example, on a cluster, but is not the best if you run, for example, the different tasks on different machines. That actually, okay, Galaxy was not designed for that. It's possible to do, but you have to copy in the Scratch directory of the workflow data each time is produced remotely, and that's could be not good in this case, especially if you want to minimize the footprint. The other points, of course, we need the checkpoints, and the other characteristic, the other requirements was completely independent by the executors. Means you can run the job whatever you want on a Raspberry Pi. Friends and colleagues did it on containers, local, using Slarm. That's what I do usually, or using clouds and even mixing whatever you want without any kind of limitation. Okay, this now is pretty common. Maybe 10 years ago was pretty new stuff. This is the architecture. This is a typical architecture of this kind of software. We have our runtime, and then the task manager, the workflow manager, and the stager. Actually, this is cool. What is cool here is about the fact that the stager is completely made in a plugin fashion. Actually, also the task, but the task is regular stuff. Even the stager. The stager is the component that understand where actual data are and where actual data have to be moved and then perform the movement. These are the components. The of DAGonStar, and some components are really stable. For example, all the batch, Slarm, and the cloud subsystem is very stable. The web tasks are pretty naive because are REST invocation, while the native tasks are usually discouraged in Dagon because for now native tasks run in the same process that the workflow engine is working. We never had the need to develop more deals because it's possible definitely run remotely Python functions, but it's not so much used here, so we never developed this. This is the when you produce something, you have the most part of the thing are just standard or maybe improved than the standard. This definitely unique. It was I'm pretty proud about the contribution DAGonStar gave to the workflow community with the workflow schema. What is the idea? I repeat, this workflow is tailored on external software. External software dealing with the other parts of the workflow exchanging files. So everything is related to the root of the Scratch directory in which the external software works. How we can refer to the external directories without be statically allocated because we don't know where are the statically where there are the files. So the idea was we consider the data produced by tasks identified by an unique ID of the workflow and a unique ID of the file of the task. Then everything is after this kind of path is related to the actual file. And then in this way, we can implement two things in a really simple fashion. One, automatically the dependencies are resolved before the workflow is executed. Two, the stager could resolve dynamically the position of the files and then provide all the need operations to move data where data is needed. More, the stager is modular, and it's possible to implement different kind of stagers. For example, at the beginning of the DAGonStar epopea, we had the stager for linked files, if we trust a lot the security of our cluster, secure copy, or even grid FTP. The other key component of DAGonStar is the garbage collector. Actually, I do like call it as my Spanish friends does, el colectador de basura. And the idea is each time a reference to a file moved from one task to another task is used, we have a counter that increments the reference. Each time the task ending the usage of this file, this reference is reduced. When the reference is 0, the scratch directory is actually removed. It's really effective, and we can manage to have, for example, the 3 days of a completely full running workflows in less than 14 terabytes. That actually is a small amount of memory if considered what the amount of data we produce. And how we define workflows? Super easy. This example is really trivial. We have the classical diamond, and we define the dependency in this way. We have the task A, okay, usual task A. Then in the task B, we just state the dependence from the file produced by A. The same for C, and D for both. This is a really trivial example. It's not an actually working example. In the next slides, we have the actual working example. But this is just to explain how it works. Once we have our workflow, we just run the workflow. This version of run is blocking. Actually, is not the only way to execute the workflow, but is the simplest and more stable way, by sure. This is the application life cycle. The diamond workflow defined in the last slide. We have first of all in the blue we have the create scratch directory operation. In orange the actual computation, and in green the staging out. As I told before, DAGonStar is based on backward references. That means the task that have to be the task that have to be going to be executed has the duty to copy in its scratch directory data it needs. In this example, task A starts, produces data, then starts B and C. When B and C finally produces the data, is removed the scratch directory A. Then D consumes D and C data, and then finally all the scratch directory are removed. Now it's just tutorial time. I share this slide, so if you want to repeat, you can repeat. It works. To install Dagon is super easy. You go to the GitHub and follow the directions, and you can directly run the demo. This is the actual example of the data flow demo with Diamond workflow. And here we have a really simple batch based task. Here the task A simply creates a directory and then copy the host name in the file F1. This is task A. Task B echo the random number on another file, and then cut it on the using the file produced by A. As you can see, the reference to the file produced by the task A is expressed as the workflow using the workflow schema. Task C the same, almost identical implementation, and finally task D that consume both data produced by C and B and C. Finally, we add the task and create the dependencies, and then run synchronously blocking fashion the workflow. And then just consider another scenario. It's only another scenario, but the scenarios are all documented in the demo on the GitHub. In this case, we have tasks that are actually Docker containers, and this is done in a really easy fashion. In this case, we use another task type. In this case, is a Docker container. As you can see, I define exactly the workflow exactly in the same way, but in this case, I use the Docker container. So we have the task A again. We have to specify the image. In this case, we don't specify its IP and usernames. The same for task B and C. In this case, we use different task types. And finally, D consumes the result. And now the extended universe, because this was just the beginning of having a tool that performed the scientific workflow execution in the shape we need. But actually, we found that there are possible other implementation. First of all, there is this in this project. In this project, this is a pretty challenging project, because in this scenario we have an on-demand workflow that is executed about each 10 minutes. And basically, each 10 minutes, WebSocket client connected to a WebSocket server, of course, receive a notification about the availability of a new weather radar image. This weather radar image is related to the whole Italy peninsula, and is managed by the civil protection. Each time a new image is received, if we already received 18 images that we could consider numbered by image -17, -16, up to image 0 is the current image. We run an inference on a model trained on over 1 year of images. In this way, the model produces 60 images. 60 images that are basically 1 hour in the future if related to the time of the latest image received. Basically, in this way, we predict in a really short time horizon what will happen in a local scale in terms of rain, in terms of precipitation. This process is called nowcasting, and nowcasting is basically one of the latest and more cool application in terms of forecasting. Because if forecasting has a temporal outlook, a time outlook of days, nowcasting has hours, but nowcasting is very accurate because based mainly on data. So in this way, we predict the next 6-10 minutes, means next hour. For each one of this data, of this weather data, weather radar data, we compute the runoff, that is basically the amount of water that's ready to be moved on the land surface after absorption and other phenomena. And then we compute the flooding using the D8 model. The D8 model runs in parallel. And in this way, actually, okay, if we have a restart of a previous simulation with a consistent flooding before running the flooding algorithm, parallel flooding algorithm again, we compose the amount of floodable water on the land surface. And this is performed each 10 minutes. That means each 10 minutes we have an outlook of some, at the end of the computation, we compute the flooding risk. And that means each 10 minutes we have an update of the flooding risk of each one of about 10,000 cities in Italy. Each 1 hour is computed reduced data file that is checked for alerts. If an alert is generated, then is the alert is broadcasted. Actually, here ends our job, and this is orchestrated using a workflow. And this kind of application is peculiar because the workflow is run automatically with a really high frequency, because it's one each 10 minutes. But if if the radar images are produced in the future with a higher frequency, for example, each 5 minutes, we have to run this workflow. And this is the another application that we use the DAGon to orchestrate to orchestrate this model called Globo. Globo is a global weather model. Was developed by the Italian National Research Council and the Institute for Atmosphere and Climate Change. And it was made by joining the BOLAM, this Bologna Limited Area Model, is a mesoscale model, non-hydrostatic mesoscale model, with another part of the model used to compute the polar areas. This model has a development history of about 30 years, maybe more than 30 years. And recently, we performed a refactoring and optimization of the source code. Actually, I was really lucky that many students of mine cooperated in this project, because it was definitely difficult to manage, because old styles of Fortran code And this is the typical example in which workflows designed to manage external software have to be as much as possible consistent and on the other side transparent, because this software have to be run in Scratch directory in a kind of a isolated environments, and really often are really demanding in terms of HTTP resources. For example, in this case, we had to completely re-implement the shared memory the shared memory communication, because the original implementation was without the collective MPI for both initialization and halos. And then the owners of the IP of the model asked us to find a way to improve the code also on a GPU, and doing that with the old code was a challenge. And finally, we succeed. And is it possible to test the model with the DAGON? With DAGON using a containerized environment, and on the project workflow and the project GitHub, there's the tutorial. And now it's the time to wrap up. And first of all, we have some contributors, and in Mexico, in Spain, at the University of Turin. In particular, with the University of Turin, we developed an ancient version of DAGON called the DAGON Capio, and we joined our effort with the effort of the University of Turin and the University of Pisa. Basically, what is Capio? Capio is a middleware that in a completely transparent way can overlap I/O operations and computing operations, basically acting both as a ad hoc file system with the in-RAM operation and as an orchestrator of operations that are connected together by a stream relationship. A stream relationship means, let's say we have two programs, two components, that one is the data source and the other one is the data sink, and both are iterative. That means for each iteration of the data source, we produce for example, a file, and this file it's possible to consume this file by the data sink. Capio is able to orchestrate this relationship and make possible to process data as is produced by the data producer continuously in a stream fashion on the data consumer. We joined this capabilities of Capio with DAGON and making another project called the DAGON Capio that is maybe could not be already ready for the prime time, but it's very promising. The tests and the results in a Cascade Founding project were really promising. Basically, we implemented the most part of the application, the full application, related to muscles, bacteria, contamination, and actually we evaluated the total amount of saving time about the 30% of about the overall. And this was a really interesting results. So maybe the next versions of DAGonStar could be directly usable in a transparent fashion with Capio. And now it's the time to conclude. We are planning to improve to develop, or better to add to the workflow other environmental application, both on demand and routinary. But the routinary is almost we will work on air quality model. Probably we will use Chimera. We already have experience with Camix in the past. Well, the DAGON has a doc file system called the DAGON FS. Now it's just experimental, but probably we should integrate in a stable fashion Capio in DAGON and try to get the best from the original DAGON file system and Capio implementation, because things have changed. We had a lot of effort in developing the interface between Capio and DAGON, so probably we will. And about that, the workflow schema has not default semantically consistent way to describe the need of streaming data. And we should think about how to standardize this. Finally, we, as told in the introduction, Steve did about me, in my institution, I am in charge the leading of the AWS Academy, and AWS is very interested in testing this kind of application on the cloud. So they could support some testing on AWS as soon. And for now is all, I think. I was pretty on time. I'm very happy about that. Oh, no. There's still one more thing. First of all, the next DAGON show will be at Works 2025 at SC25 on November 17th. The paper is about a DAGONStar. The speaker should be Dante, that should be connected, and from the University of Madrid, Carlos III. And finally, the big news is about the eScience Conference 2026. It will be in Naples, Italy, September 28th, October 2nd. And of course, it will be in the DAGONStar layer. So yeah, we will see nice things. And now it's the end, the actual end. Thank you so much.